Montpellier, south of France. And I will address the issue of reasoning on data, and more specifically, I will consider the problem of ontology-mediated query answering, which is a problem that attracted much interest in the last 10 years. So first, I will adopt the viewpoint of a researcher in knowledge representation and reasoning, which is a subfield of artificial intelligence and historically at the heart of artificial intelligence. And in this domain, we study formalisms to represent various kinds of human knowledge and do reasoning on these representations. And generally speaking, the higher the complexity of a formalism is, the higher the expressivity of a formalism is, the higher is the complexity of reasoning. So what we try to do is to find good trade-offs between expressivity and computational tractability. And generally, KR formalism, or I will also say language, are based on logic, and since we do automated reasoning, it is computational logic. And in this talk, I will consider classical first-order logic and very basic logical notion. So I have divided the talk into 3 parts. I guess the second one is it's the longest. In the first part, I will present the basic notion, knowledge bases, ontologies, how we can view queries and data from a logical viewpoint. Briefly, the main KR formalisms to represent and reason with ontologies, and the ontology-mediated query answering, and I will try to motivate the interest of this approach. Then I will present in more detail the KR formalism, which are description logics, and especially on description logic, and some rule-based languages, and I will focus on existential rules, which is a rather new framework to represent knowledge and do reasoning. And I will also present the main algorithmic approaches to solve ontology-mediated query answering. And in the last part, I will address decidability issues. So I don't know if everybody here is, or is there here someone who doesn't know at all what an ontology is? Or because I have planned to spend some time on presenting ontologies, so maybe I can go quickly if you already know it. Well, anyway, feel free to interrupt me, and I will pass quickly on some slides, but if you want, we can stop. So first, a fundamental notion is that of a knowledge base and a knowledge-based system. In a knowledge-based system, we have 2 components. We have a knowledge base and we have reasoning services. And in a knowledge base, there is a fundamental distinction between 2 kinds of knowledge: general knowledge on the application domain. Like if you are interested in animals, we can say cats are mammals. And in today's system, this general knowledge is represented in what we call an ontology. And the other kind of knowledge is factual knowledge, which is specific knowledge about particular individual situation, observation, like Felix is a cat. And this kind of knowledge is encoded in a fact base. And for now, we can say that a fact base and a database are more or less the same notions. I will detail later. And the knowledge encoded in the knowledge base is expressed in a knowledge representation language. This knowledge representation language is also a reasoning language, and it is provided with reasoning algorithms that allow us to solve some fundamental tasks, like checking the consistency of the knowledge base. And in logical terms, the consistency is the satisfiability of the knowledge base, or computing answers to a query over the knowledge base. And so the knowledge-based system provides generally high-level reasoning services that rely on these fundamental tasks. So what is an ontology? So maybe I will go a bit quickly on these slides. But an ontology in computer science, because there are many meanings of ontology depending on the domain, in computer science we can say in a nutshell that it is a formal specification of the knowledge of a particular domain. And the important here is formal specification because it allows for machine processing that relies on the semantics of knowledge, so it allows for automated reasoning. And in this specification, we have a vocabulary that will be described in terms of concepts and relations. And we have semantic relationship between the terms of the vocabulary. So just a few examples of ontologies, because nowadays you have hundreds of ontologies in almost any domain. But the precursors were medicine and life science, and there are hundreds of available ontologies just in these domains, which have been carefully built with experts of the domain. And a good example is maybe the most well-known ontology is NOMED CT. CT means clinical term. It's an ontology that aims at representing all the clinical terms used in medicine. And now it has about 400,000 terms. A bit smaller one is Galen, which is well-known too. And then you have specialized medical ontologies like FMA in anatomy, NCI in cancer. And you also find ontologies in biology, agronomy, and other science. And the information systems of large organizations like ministries and large corporations are more and more organized around ontologies. Yes?
Just to understanding, that means that ontology in this topic is not, it's really big data bank for a special.
I will detail. I will detail what an ontology is, okay. And maybe you can ask again your question if it is not clear. Okay. Okay. So let's go into detail. So what do we find in ontologies? At the core of ontologies, we have concepts or classes. So a concept or a class is a category of entities that share some common properties which are meaningful for the application we are developing. So in first-order logic, a class or a concept will be a unary predicate, like cat or mammal. And then you have instances of classes, which are specific members of these classes. And in first-order logic, it will be a term, a variable, or a constant. And we will not consider function symbols here. And there is a fundamental relation on classes, which is called a specialization or subsumption, or is a kind of a subclass of. And when we say that C1 is a subclass of C2, it means that every instance of C1 is also an instance of C2. And in first-order logic, we will translate this by this formula for all x. If C1 of x, then C2 of x. For instance, all cats are mammals. So here is a small extract from the ontology I told about SNOMED City. So for instance, here you have the concept that describe a disease. A disease is a disorder, then it is specialized into lung disease, infectious disease, then into pneumonia. An infectious pneumonia is both pneumonia and an infectious disease. In infectious diseases, you find a bacterial disease, viral disease. And here you have Legionella, who is a kind of bacterial pneumonia, which is an infectious pneumonia, etc. And you have here, for instance, organisms, which are specialized into infectious agents. And you have two kinds of infectious agents, which are bacteria and viruses. So at the heart of an ontology, you have concept organized by specialization. And for many people, an ontology is just this. But actually, an ontology is not just a classification. It is much more than that. What do we have in an ontology? Well, I said that an ontology specifies the vocabulary of an application domain and the semantic relationship between the terms. So here, from the vocabulary, we have seen concepts, and we have seen the subsumption relation. But you have also in a vocabulary, you have also relations, which are the relations that can stand between instances of concepts. You have semantic relationship between relations. You can describe the properties of concepts, the properties of relations, and other axioms that more generally express domain knowledge. So let's consider the relation between instances. So often these relations are binary. They are called roles in description logics or properties in the semantic web. And these relations are also organized by a relationship, which is a sub-relation relationship or specializations. And for instance, if we take two relations from a SNOMED city, we have that the relation as causative agent is a specialization of due to, which means that for all x, for all y, if x has causative agent y, then x is due to y. And then on relations, we generally have signatures, and a signature of a relation assigns a maximum concept to each argument. So it's a classical notion. And in the semantic web, we call that domain and range. So for instance here, if you look at SNOMED city, you will see that as causative agent has for first argument a disease, and for second argument an organism, which means that if x has causative agent y, then x is a disease and y is an organism, or a specialization of these classes. So this gives this formula for all x, for all y. If x has causative agent y, then x is a disease and y is an organism. So we have seen the two components of our vocabulary, concepts and relations. And then you can have many kinds of different axioms. So here I only listed the most frequent one. Fundamental relationship between concept and relations is disjointness between this concept or this relation. For instance, we can have two concepts, bacteria and virus, and we want to say that there are no instance, no object, which are instances of both bacteria and virus. And we will express this depending on the KR language considered. The associated formula will look like this for x. If x is a bacteria and x is a virus, then we have an absurdity. This is the always false symbol. Or equivalently, for x, if x is a bacteria, then x is not a virus. So, and more generally, we can express negative constraints that forbid some situation to happen. We can also express necessary or sufficient properties of concepts. Like we can say that if any bacterial disease is caused by a bacteria, which will be expressed like this in logic for all x. If x is a bacterial disease, then there exists y, such that y is a bacteria and x has causative agent y. Then we often express properties of relations. So inverse relations are very convenient. So we just say that some relation at the inverse of each other. Like here, as part and is part of for x plus y. If x has part y, then y is part of x. We can express a symmetry, transitivity, and another very frequent axiom is a functionality axiom for especially for a binary relation. So it's, for instance, assume that it is true for the relation is part of. For all x, for all y, for all z. If x is part of y and x is part of z, then y is equal to z. So it means that something can be part of, something cannot be part of two different things. So we had a quick overview of the frequent axioms in ontologies. Now, what kinds of languages are used in practice to express ontologies? So in the semantic web, we have several kinds of languages to express ontologies, and the simplest one is called RDF schema or RDFS. And in this language, you only have hierarchy of classes, hierarchy of binary relations that are called properties, and you have signatures for these relations, which is the domain and the range. And that's it. So it's a very simple language. Then you have more explicit fragments of first-order logic. So typically description logics, which are languages that were really developed for representing ontologies. And you have also many rule-based languages. So I list the most used ones. So Datalog, which is a deductive language of relational databases. Existential rules, I will detail later on this language. And if you attend the talk by Marie-Christine Rousset on Thursday, I guess, she will talk about RDF. So RDF is a language to describe objects in the semantic web. So RDF deductive rules. And you may also consider answer set programming, etc. So from a strict logical viewpoint, an ontology is composed of a vocabulary, which is a finite set of predicates to express concepts. These are unary predicates, and relations, which can be in general of any arity. And then you have a finite set of formulas over these predicates, and these formulas are closed, which means that there are no free variables. And these formulas are of the form for all x, if some condition of x here is a tuple of variables. So for x a tuple of variable, if some condition of x, then some conclusion on x. And here a condition and conclusion may also use other variables than the x. So, it's okay? Yeah. Okay. So now, what are ontologies good for? Why do you care about ontologies? So the first thing is that an ontology provides a common vocabulary. And it is very important in scientific domains when you have several experts from different domains. It's easier to share information if you normalize the vocabulary. Another interest is that since it is a formal specification, it constrains the meaning of the terms. So it forces to explicit things that would not be said or that would remain implicit. And it forces to remove ambiguities. And there are less misunderstandings between people. So that's a point, but maybe it's not the main one. The interesting is that we have knowledge representation and reasoning language. And this language is to do automated reasoning. And this can be the basis of very high services. So for instance, we can find implicit links between pieces of knowledge that were not explicitly connected. We can check the consistency of a knowledge base. So this is a very classical task. Check if there are no errors in modeling. And the third point, which is less classical and that I will develop today, is that we can enrich data query answering. I will illustrate this on a small example. So assume we are in an hospital. This hospital manages records about patients, so medical records. This record are stored in a database, which may be a relational RDF, NoSQL, or whatever. So we have data about patients stored in a database, and this data is fed by the doctors, or at least information coming from the doctors. And this information tends to be very specific, like we can have that the patient P. For the patient P, the diagnosis is Legionella. Or it can be, of course, even more specific than that. And now, assume there is an administrative person in this hospital who wants, for some investigation purpose, find all patients affected by a lung disease due to a bacteria. So if we only have databases, first it will be very difficult for this person even to formulate a query, because the language he or she wants to use is not the language that the vocabulary she wants to use is not the vocabulary that has been used to structure the data. So first there is a mismatch between the vocabulary. The user here wants to use a very general vocabulary, while the data have been structured for other purposes. And second, if you have some knowledge, basic knowledge in medicine, you will agree that Legionella is a kind of lung disease due to a bacteria. And so the patient P should be, intuitively, should be an answer to this query. But to find the patient P, to retrieve the patient P as an answer, we have to do some inferences and to use some medical knowledge. And it is not possible to do this with a simple database, because in databases you can make very sophisticated, so databases are able to answer very sophisticated queries, but you can only find what has been explicitly stored in the database. So here, for instance, what are we missing? So we will need some, to retrieve this patient P, we will need some medical knowledge, like, for instance, coming from SNOMED City, like a Legionella is a bacterial pneumonia is a pneumonia is a lung disease. A bacterial pneumonia is caused by a bacteria. If X is caused by Y, then X is due to Y, because you see we have due to. And some knowledge that if the diagnosis for a patient X contained a disease Y, then X is affected by Y. So the idea here is to go from the notion of a database to that of a knowledge base. And what is a knowledge base here? It is a database with an additional layer, which is the ontologies. And what we want to query is the knowledge base. That is, we want to query data while taking into account the inferences enabled by the ontology. So more generally, that's why. So the problem we have now is called ontology-mediated query answering. And what are the advantages of adding this ontological layer on top of data? So the first thing we have seen in the example is that it allows to enrich the vocabulary to, in order the user to use terms that are familiar to her. And it allows to abstract from a specific data storage. The second thing is that it allows to infer new facts that were not explicitly stored in the database, but which can be inferred by the ontologies. And the third advantage is that it can provide a unified view of multiple sources. So for instance, we can have several hospitals. Each hospital has its own database, and we want to provide the user with a unified view of these databases. So if we come back to our example, I said we would need some knowledge to infer that the patient P is an answer to the query. So what does this knowledge look like in logic? So a Legionella is a bacterial pneumonia will be like this for X. If X is a Legionella, Legionella could be an instance, but in SNOMED City it is a class. So it is a unary predicate here. So if X is a Legionella, then X is a bacterial pneumonia, and with a similar kind of knowledge. A bacterial pneumonia is caused by a bacteria. For all X, if X is a bacterial pneumonia, then there exists a Y, such that X has causative agent Y, and Y is a bacteria. If X is caused by Y, then X is due to Y. For X for Y, if X has causative agent Y, then X is due to Y. And finally, if the diagnosis of a patient X contains a disease Y, then X is affected by Y. For X for Y. If diagnosis X, Y, and disease of Y, then X is affected by Y. So we have seen what an ontology is. And we have three components in our problem. We have the knowledge base composed of an ontology. There is also a fact base, and there is also a query. So I will now talk a bit about fact bases. So usually in knowledge-based system, a fact base is a set of ground atoms. So ground means without variables. So here atoms and constants. And these ground atoms use the ontological vocabulary. So the concepts and the relations we have introduced in the ontology. For instance, to say that the diagnosis for the patient P is Legionella, we may write patient of P, diagnosis PM. So M stands for some particular Legionella and Legionella of M. And importantly, a relational database can be naturally seen as a fact base if we see it from a logical viewpoint. Because what do we have in a relational database? First, we have a relational schema. And from a rather abstract viewpoint, what is a schema? It is given by a finite set of relations and an infinite set of, which is a domain for the values that can occur in the database. So in a relation from the database schema is translated into a predicate with the same arity, and a value is translated into a constant. Then an instance of a relation R in a relational database is a table. It is a finite set of tuples on this relation, so this corresponds to atoms on our predicates. So for instance, here we have a table with two attributes. So we have a relation R with two attributes, attribute 1, attribute 2. And we have three tuples, A1, A2, A2, A3, A1, A1. So in logic, we will translate this into three atoms, one for each line of the table. So R of A1, A2, R of A2, A3, R of A1, A1. And then a database or database instance to distinguish it from the database schema. It is a set of instances for each relation. So this corresponds to a fact base. It is finally a set of ground atoms. So now I talked about queries. So what kind of queries I will consider here? Actually, what people consider as fundamental database queries are conjunctive queries. This also corresponds to the most frequent queries in a relational database system. So, for instance, in my example, we wanted to find all patients affected by a lung disease due to a bacteria. This could be written like this, using the vocabulary we have introduced. Q of X means this query wants to find all X, such that there exists Y, there exists Z. X is a patient, X is affected by Y, Y is a lung disease, Y is due to Z, and Z is a bacteria. So more generally, a conjunctive query is an existentially quantified conjunction of atoms. There may be free variables. If there are free variables, these variables are called the answer variables. These are the variables for which we want to find values in the database. And if you have no free variables, it is a closed formula, and then it is a Boolean conjunctive query, which admits an answer yes or no. And this logical form of a query actually corresponds to the core of queries in many querying languages used in practice. So first, for datalog. I don't know if datalog is really used in practice, but if we consider datalog, conjunctive query is a single rule where you find the query itself as the body of the rule, and in the head of the rule you have a special predicate, here answer, which gathers the answer variables. Conjunctive queries also correspond to select joint project queries in relational algebra. So it's In SQL, we would this corresponds to queries of the form select, from, where, and then join conditions. And if we consider Sparkle, which is now widely used in the semantic web area, the core of Sparkle is called basic graph pattern query, and a basic graph pattern query is exactly a conjunctive query. It is a query of the form select, something where, and then you have a basic graph pattern that you have to find in the data. Now, what is an answer to a conjunctive query? Well, if it is a Boolean conjunctive query, the answer is yes, if the query is entailed by the fact base. That is, every model of the fact base is a model of the query. Now, consider we have a conjunctive query with answer variables x1 up to xk, then a tuple of k constants is an answer to the query with respect to a given fact base if, when we instantiate this variable by the corresponding constants, we obtain a Boolean query, because these were the only free variables in the formula. So we instantiate the formula, the free variable by the constants, we obtain a Boolean query. And then this tuple of constants is an answer to the query if the instantiated query is entailed by the fact base. And how do we compute this? Well, a fundamental notion, really fundamental notion for all this talk is that of a homomorphism. So I don't know if everyone is familiar with this. It's a very basic relation between structures in algebra. Generally speaking, a homomorphism from a structure to another is a mapping from the elements of the first structure to the elements of the second structure that keeps the relationships between the elements. So here, let us consider that the fact base F and Q are a set of atoms. A homomorphism H from Q to F is a mapping from the variable of Q to terms of F. So if F is composed only of ground atoms, these terms are constants. But more generally, we may have constants or variables. So it's a mapping from variables of Q to terms of F such that if we apply this homomorphism as a substitution, so we replace each variable by the corresponding term, we obtain a subset of the fact base. That is, we can find the query as a subset of the fact base. And the fundamental relation is that a query is entailed by the fact base if and only if it can be mapped to this fact base by homomorphism. And a tuple of constant is an answer. A tuple of k constant is an answer to a query with k answer variables if and only if there is a homomorphism from this query to the fact base that maps each variable xy, xi to the constant ai. So for those who may not be familiar with this notion, a very, very simple example. So assume we have a fact base here with 3 movies, M1, M2, M3, 3 actors, A, B, C. We know that A plays in M1 and in M2, and C plays in M3. And then we have a query which wants to find all X, such that there is Y is a movie, and X plays in Y. So we can find here 3 homomorphisms from the query to the fact base. So when we look for homomorphism, we see the query as a set of atoms. So we look for homomorphism from this to this. And we have 3 homomorphisms. The first homomorphism maps X and Y to A and M1. The second to A and M2. And the third one to C and M3. And we see that in each case, if we replace the variable by the image, we obtain a subset of the fact base. And then the answers to the query are obtained by restricting the domains of the homomorphism to the answer variable. So here we have 2 answers, X equal to A and X equal to C. So if we come back to our medical example, we want to find all patients affected by a lung disease due to a bacteria. So this is the logical form of the query. We have a fact base, which says that the diagnosis for the patient is Legionella. So what do we need to answer this query? We can see that there is no homomorphism from the query to the fact base. But we will try to infer new facts from the ontology. So we know that Legionella is a specialization of lung disease. And M here, which is a Legionella, is also a lung disease. Legionella is also a specialization of bacterial disease and of disease. So M is also a bacterial disease, a disease, etc. We know that a bacterial disease has a causative agent, which is a bacteria. So we know that M has a causative agent that we call B, because we have to invent a new individual that is not, which is not in our fact base. We call it B. M has causative agent B, and B is a bacteria. We know that as causative agent is a specialization of due to, so M is due to B. And we know that if X is diagnosed with Y, which is a disease, then X is affected by Y. So since M is a disease and P is diagnosed with M, then P is affected by M. And if we take the fact patient of P and all these facts that we have inferred from the ontology, now we can find a homomorphism from the query to the enriched fact base. It does not mean that we will actually compute answers like this, just to explain the semantics of answers. So now, for now, I have considered only this, so a query, an ontology, and a fact base. And the important is that the fact base uses the same vocabulary as the ontology. But we can consider a more general schema, which in the domain is called ontology-based data access, which is the following. We do not only have a fact base, we want to access several data sources or databases, if you prefer, which are independent, which have been conceived for many purposes, absolutely independent from our application. And these data sources can be in a heterogeneous format. And we want to exploit this data. So what we add to our schema is this notion of mappings. So we will have a set of mappings that allows to go from the data to the fact base. And a mapping is something like this. On the left, you have a database query that will extract data from the database. And this produces fact from the fact base. And the idea here is that, the idea is the following. Nowadays, we have many sources of data, and we want to exploit them for a specific application. So, at a conceptual level, we will build an ontology which describes the application domain with a very high level of abstraction. We will have a fact base, and here I have explained that the fact base is obtained by extracting data, but actually this fact base, we will see, can stay virtual. So it's just to explain, but we may never actually build this fact base. So we have a fact base using the vocabulary of the ontology, and the user is able to formulate query in the ontological language, which is very abstract and very high level with compared to the data language. And then the answers to the query are inferred from the knowledge base. So if I take again my example, oh, what is that? Sorry. I don't know. So we should have two tables here. It's a bit strange. I will I will check. Should be this. Okay. We will try again. Ah, it's better. Okay. So we come back to our medical example, and we assume that we have store the data in a relational database with two relations, which are called patient T and diagnosis T. In the first relation, we have three attributes: an identifier for the patient, the name of the patient, and for instance, a social security number. And in the second table, we have again the identifier for a patient and a disorder. And here we have the vocabulary of the ontology, which has in particular these predicates, a unary predicate, patient, Legionella, and a binary predicate, diagnosis. And the role of a mapping is to go from the data that are stored in the database to facts expressed using the ontological vocabulary. And generally speaking, so it is a database query with some answer variables, x, and then, so this is the left part, and in the right part, we have a conjunction with three variables, x. For instance, here we could have this, a first query, q of x, which wants to find all x such that there exists n, there exists s, such that in the patient table, we have x and s. And if we find this, if we find a value for x, we can build the fact patient of x. And the second queries ask for all x, such that there is n, there is s. We find this tuple in the patient table, x and s. We find another tuple in the diagnostic table, diagnosis, should be diagnosis, with the same x and y as the value Legionella. Then we can build two facts using the vocabulary of the ontologies, which are diagnosis of x, z, and Legionella of z. And you can see here that z will be a new individuals that may not be a constant. It may be an existentially quantifier variable. So in our example here, we can assume that in the patient table, we have this patient P. P is the identifier. In the diagnosis table, we have P and the disorder Legionella. And from these two mappings, we will extract the facts, patient of P, diagnosis of PM, and Legionella of M. So now we have seen the main components of the ontology-mediated query answering problem. So we have a knowledge base composed of an ontology and a fact base. We want to query this knowledge base. And most work in the area consider conjunctive queries, possibly Boolean conjunctive queries. We have a logical theory, a set of formulas in first-order logic, so in a suitable fragment of first-order logic. And the fact base is a set of ground atoms, or more generally, an existentially closed formula. And the fundamental decision problem, if we consider that Q is a Boolean conjunctive query, and theoretically we can do this without loss of generality, the fundamental decision problem is to determine whether Q is entailed by the ontology and the fact base, where here, when I write OF, it means we take the formulas of O and the formulas of F. So this is, we have finished with the basic notion. And now I would like to present the main KR formalism and algorithmic approaches. I will give a brief outline of description logic. I don't know, everybody here knows the description logic? No? Okay, so it will be useful. So an outline of description logic, and I will explain why we generally focus on horn description logics when we want to query data. I will present existential rules, and then two approaches to query answering, which actually are very related to classical approaches and rule-based systems, which are forward chaining and backward chaining. But in this context, we call this materialization and the query rewriting approach. So let's begin with description logic. So description logic is a family of languages that have been really designed to represent ontologies and reason with ontologies. And the first such languages were born at the beginning of the 80s. And they mostly correspond to decidable fragments of first-order logic. They are also related to modal propositional logic, to the guarded fragment of first-order logic, etc. And one characteristic is that there are no variables at all in the syntax. It's a variable-free syntax. And at the beginning, these languages were called concept languages. Why concept languages? Because the idea is that we start from concept and role names, which correspond to unary and binary predicates in logic. We have a set of constructors, and with these constructors, we can build complex concepts. And at the beginning, description logic were really focusing on concepts, and since a few years, they are also considering complex roles. And then an ontology is a set of axioms that state inclusion between possibly complex concepts and possibly between roles.
Sorry, please repeat variable-free syntax. You mean only predicates or what?
You will see. Well, I will show you just now. Actually, there are no. It is translated into logic, but when you use the description logic syntax, you have no variable at all. You will see right now. So we start from a vocabulary in terms of atomic concepts and atomic roles, so it's just names. For instance, human, parent, students, these are the concepts, unary predicates. And we have binary predicates like parent of, sibling of, etc. Then, for each particular dialect of description logic, we have a set of constructors to build complex concepts. So it really depends on each particular description logic. So among these constructors, you can have conjunction. For instance, starting from a human, well, I need several constructors here. So you can have conjunction, you can have disjunction, you can have negation, you can have restricted form of existential and universal quantification, and you can have the inverse of a role, a composition of roles, etc. I just listed the main ones here. So for instance, if you have the names human and parent, so two concepts, you can build the complex concept, which is human and not parent. So this concept denotes all the objects which are both human and not parent. Another complex concept can be female or male. So it is a set of all individuals who are female or male. And here, it's a bit more involved. Exists parent of dot female and students means that it is a set of all individuals which are the first argument of a role, so a binary relation parent of, and the second argument is a female and a student. So this denotes the set of all individuals who are parents of a female or a student. And this one, for all parents of dot male, denotes all individuals such that each time they are related to another object, or the same object, why not? Each time we have their first argument of a role parent of, the second argument is of type male. So those who are parents of male only, or maybe not parent at all. Each time they are parents of an object, this object is a male. And here is another example. X is parent of minus. It denotes the set of all individuals, so a concept, such that there are second arguments. The minus is to inverse the argument. They are second argument of a parent of role. And here we can compose two roles. So this denotes the individual X and Y, such that X is parent of Z, and Z is parent of Y. So this corresponds to the grandparent relation. So it's not very important to understand the detail. It's just to explain the approach of description logic. So we have atomic concept, atomic relations called roles. We have constructor to build complex concepts and roles. And then, logically speaking, to each concept is assigned a first-order formula with a single free variable x. So human corresponds to all x which are human. So x is a free variable here. Human and not parents, human of x and not parent of x. X is parent of dot, female, and student. So X such that there is Y, X is parent of Y, Y is a female, and Y is a student. For all parents of female, so X such that for all Y, if X is parent of Y, then Y is a female. So to each concept we assign a formula with a single free variable X, and X is the name taken to talk about all the individuals that are in the concept. And to each role, we assigned a formula with two free variables. So here, X and Y. So instant parent of composed with parent of will be all X and Y, such that there exists Z, X is parent of Z, and Z is parent of Y. So we build a complex concept, and then what is a knowledge base? So a knowledge base has two components. You will not be surprised. An ontology and a fact base. But in description logic, the ontology is called a T-box, and T stands for terminological box. And an A box, A stands for assertional box. And in the T-box, so in the ontology, we have axiom of the form C1 is included in C2, which means that actually, it means that all instances of C1 are also instances of C2. And R1 included in R2 means that if X is related by R1 to Y, then X is also related by R2 to Y. And in logics, this corresponds to this formula for all X. Full, I wrote full of C1. It means the full translation of the concept C1 with a single free variable X. So for all X, if C1 of X, then C2 of X, where C1 and C2 can be actually complex formulas with a free variable X. And for the whole, for X for Y, if R1 between X and Y, then R2 between X and Y. So I don't know if I will list all this, but we can say, for instance, that human is included in male or female, which means that for X, if X is a human, then X is a male or a female. Adult is included in not child, which means that these two concepts are disjoint. So for X, if X is an adult and a child, then there is a trouble. We have an absurdity. Parent included in it exists parent of, which means that for X, if X is a parent, then there exists Y, such that X is the parent of Y. So this is the concept parent, and this is a relation parent of between two individuals. Is it clear? So if we now, happy father included in for all parented dot female. What does it mean? It means that for X, if X is a happy father, then for all y, if X is parent of Y, then then Y is a female. So it means that the set of happy father is included into the set of those who are parents of female only. Or this one, human included in exists parent of minus dot human. It means that for all X, if X is a human, then X is then there exists Y, such that Y is parent of X. We don't have XY but YX because of the minus sign. Y is parent of X and Y is a human. So it means that every human has a parent who is a human. And so last example with the composition of role, parent of composed with parent of included in sister of. For all X over Y, if there exists Z such that X is parent of Z and Z is parent of Y, then X is ancestor of Y. So this is the T box. You have axiom of this form. And in the A box, we have a set of ground atoms, so a classical fact base. So what can we do with this? In description logic, there are some, for years, there have been some standard reasoning tasks, which are, well, these tasks actually are very closely related. And we can consider, for instance, these ones. Concept subsumption. We have two concepts, C and D, and we would want to know if from the T box, it follows that C is included in D. So the T box entails that every individual of type C is also of type T. And this allows to do classification, that is to find all subsumption relationships between concepts, even if they were not explicitly encoded in the T box. We have concept satisfiability. Given a concept, is it satisfiable with respect to the T box? And satisfiable with respect to the T box means, is it possible that this concept is non-empty? Is it possible that it has an instance given the T box? Because, of course, when we model knowledge, we don't want to have concepts that are necessarily empty. Knowledge-based satisfiability, given a T box and an A box, is this knowledge base satisfiable. And instant checking, we have a constant B, and we want to know if it follows from the knowledge base that B is of type C. And so actually all these tasks are very related, and they can, for instance, all be expressed in terms of knowledge-based satisfiability or unsatisfiability. So here I refer to this problem. Is the knowledge base satisfiable? So each task can be translated into another task, provided that the considered description logic has the right constructors. For instance, concept subsumption, given C and D, does the T box entail that C is included in D, can be expressed as, is the knowledge base composed of the T box and the A box, which is restricted to C of A and not D and A, is this knowledge base unsatisfiable? So this is basic logic, but if you want to express this in a description logic, you see that we have to, this description logic must offer the negation. Otherwise, we cannot do the translation. Concept satisfiability, is C satisfiable with respect to the T box? Well, this is true if and only if we consider the T box, we consider the A box restricted to a single individual C of A, and we check if it is satisfiable. And instant checking, so if C of B entailed by the knowledge base, well, again, this is classical logic, we take the A box, we add, I think I wanted to say not C of B. You add not C of B to your A box, and you check if it is unsatisfiable. So these were the standard reasoning tasks in description logic, but then, as you know, the data arrived. So people were interested in querying data. And so they wonder, so we have standard reasoning tasks. Can we answer complex queries with these standard reasoning tasks? And the problem is that the only query we can formulate with these talks is instance checking. We have a constant, and we want to know if it is of a given concept, and that's it. And unfortunately, query answering with conjunctive query cannot be reduced to these talks. So this led to new description logics with new algorithmic techniques. I will explain that now. So let's start from the standard expressive description logic, which is called ALC. So it was up to 10 years ago, it was the classical description logic with standard reasoning. So in this description logic, we can express top, atomic concept, conjunction of concept, exist R.C, so restricted existential quantification, negation of a concept. We can have the disjunction between two concepts, and for R.C. Actually, these two last forms can be expressed with the previous one, because, as you know, a disjunction can be expressed with negation and conjunction, and the for all can be expressed with existential quantification and negation. So in ALC, you have this, and in the T-box, the axiom of the T-box are a concept inclusion. There is nothing about roles. And with this standard description logic, the basic tasks of satisfiability and instance checking are already X-time complete in combined complexity. I have to explain the distinction between combined and data complexity. So, what do I mean here? When we consider query answering problem, we consider two complexity measures. So we have our problem. We have a knowledge base with an ontology of fact base. And we have a query, and we want to know if the query is entailed by the knowledge base. If we consider combined complexity, it is the usual complexity. We consider that the input is O, F, and Q. So usual complexity. And if we consider data complexity, we consider that O and Q are fixed, and the only part of the input is F. Why is that? Actually, this distinction comes from databases. It follows from the remark that, so in databases, we didn't have the ontology. We only have a fact base, a database, and a query. And it follows from the remark that the query is very small with respect to the data. So the size of the query is negligible compared to the size of the data. So it makes sense to consider that the input is only composed of the fact base. And for instance, if we consider the basic query answering problem in databases or fact bases, so I have just a Boolean conjunctive query and a fact base. I want to know if the query entails a fact base, and this can be done with a homomorphism check. I have to check if there is a homomorphism from the query to the fact base. So this is NP complete in combined complexity, because, well, it's easy to see that it's not polynomial. Or it is NP complete, I will say. And it's easy to see that if we consider data complexity, it becomes polynomial. Why? Because if you take a brute force algorithm, you can generate all possible mappings from the variable of the query to the fact base, and then you can test each mapping to see if this mapping corresponds to a homomorphism. And if you do a brute force algorithm like this, you have an algorithm which is exponential in the size of the query. in the number of variables of the query. But if you are in data complexity, you consider that the query is fixed, so its size corresponds to a constant. So then you have an algorithm which is exponential with a constant, so it is polynomial. So if I come back to description logic, so we consider the standard expressive logic ALC. So satisfiability and instant checking, which are standard reasoning tasks, are already X-time complex in combined complexity and co-NP complete in data complexity. And actually, this is not good news at all when we consider data complexity. And if we add the possibility of having the inverse roles, then these talks become even 2 X-time complete in combined complexity. So this may be reasonable if we only have an ontology and a small A box, but as soon as we have large quantities of data, we cannot offer to have this complexity. And actually, 2 factors led to the evolution of description logics and the birth of new description logics. So one thing is that so people from description logic developed tools, and tools were used by practitioners who developed true applications. In particular, Snowbell City is described with a description logic. And from practical use, it appears that actually people were not using all these constructors. In practice, people were using essentially conjunction and existential restriction. And of course, the complexity is much smaller if we have only these quantifiers. So this led to a new description logic with only conjunction and existential quantification. And the other factor is that, as we have seen, the complexity is too high for query answering on large volumes of data. So the last 10 years, we saw new description logics with lower complexity. So they are less expressive, but they have lower complexity. And two prominent description logics are the DL-Lite family, and in particular a logic called DL-Lite R, and EL. So what do we have in this description logic? So DL-Lite R was from the beginning conceived to do query answering on large A boxes, that is large amount of data. And it's very simple because we can only have inclusion between concepts which are of the form atomic concept or exist S, that's all. Inclusion of a concept, so B1 included in node B2. It seems that we have a negation here, but actually it's not true negation. It only says that B1 and B2 are disjoint. Because if you, from B1 you conclude that if you have an individual of type B1, you conclude it is not of type B2. Since you don't have a negation anywhere else, you can do nothing with this information. You can just conclude that if an individual is both a B1 and a B2, then the knowledge base is not satisfiable. That's it. So you cannot use this information for query answering. So we have so we can forget about this. We have inclusion between concepts which are very simple, atomic concept, and we have existential quantification, or we can have inclusion between roles, and the same as here, disjointness between roles. And a role is either a role or the inverse of the role. And the second logic is EL. And each time I present one member of the family, but then we can have some additional descriptor, and you obtain a whole family of description logic. So in EL, you only have inclusion between concepts. So this logic has been modeled from the use of the experience acquired with the modeling of Snowbell City. So you have inclusion between concepts, and a concept can be either top or an atomic concept or a conjunction of two concepts, or you have existential quantification, exists R dot C. And this logic has been designed to do classification, so standard reasoning with large T boxes. And the common feature of both description logic is that there is no disjunction and there is no true negation. And the property, the fundamental property ensured by this restriction is that each satisfiable knowledge base has a unique canonical model. And then for any Boolean conjunctive query, we have that the query is entailed by the knowledge base if and only if this unique model is the model of the query. And checking if M is the model of the query is just a homomorphism check. And so we had a new generation of description logic, and the reasoning techniques for this description logic are very similar to forward and backward chaining in a rule-based system. So completely different from the techniques that were used before and that were rather relying on tableau techniques, for instance. So I will, I think, okay, we have half an hour. I was wondering about the time. So we still have half an hour. I will just give a small example to explain why disjunction or negation introduces some complexity of reasoning when we want to answer query. So here I have a very simple situation. I have three cubes, or three objects, A, B, and C. A is blue. We don't know the color of B, and C is not blue. And in the T-box, so in our, the concepts are blue or other, which means another color. And we have one role which is on. So in the fact base, we have that A is blue, C is other, A is on B, and B is on C. And we ask the query, is there X, is there Y, such that X is blue, X is on Y, and Y is other. And we can see here that we have no homomorphism from the query to the fact base. And assume that in the T-box, we have the information that everything is either blue or other. So what do you think the answer to the query is? Is it yes or no? Is there, are there objects X and Y, so that X is blue, Y has another color, and X is on Y? Yes, this is one. Why is it? Why is the answer to the query yes? Because of this axiom. We know that everything is either blue or has another color. So we have to do a reasoning by considering different cases. That's why we have, if we have many cases, we have a combinatorial explosion. So here we have to consider two cases. We say, we know nothing about B, but either B is blue or B is other, because the knowledge of the T-box is that everything is blue or other. So if B is blue, then we have an answer to our query by taking B and C. If B is other, we have an answer to our query by taking A and B. So in all cases, in all possible words, in all extension of the fact base that satisfies the T-box, we have a yes answer to the query. So you see that even very simple axiom with a disjunction, and it is the same for negation, introduces some combinatorial explosion. So it will be the same if we replace this axiom by this one. Not blue is included in other. But actually, it's really equivalent in a logical term, because it means that for all x, not blue of x or other of x. But I want to point out that if we have this, like it was, we could do in the description logic DL light R, if we say that other is included in not blue, this is absolutely not the same complexity as this. Because here, we only say that other and blue are disjoint concepts. So if we have something that is other, we can conclude that it is not blue, but then with this information, we can do nothing because the query is positive, the A box is positive, so it's only a disjoint net constraint. So this is only a disjoint net constraint. This is really something that introduces some added complexity. Question? Can I continue? So in summary, in a description logic ontology, so a T-box, we have axiom of two forms. For all x, so we have inclusion between concepts, which is translated into for all x if a formula associated to C1 with a free variable x, then another formula associated with C2 with free variable x. And similarly for roles, for x, for y, if R1 between x and y, then R2 between x and y. And here R1 and R2 are either atomic roles or the inverses, or a composition of atomic role and inverses if the description logic allows for it. And an important property is that description logic satisfies the tree model property. What does it mean? It means that if a knowledge base is satisfiable, then it has a model which is tree-shaped. And this explains that the complexity can be lower than in some other fragment of description of first-order logic because of this tree-shaped property. And I presented some new DLs, which are DL light and EL. And with these new DLs, the left and right part of the implication here for concept are existentially quantified conjunction of atoms. And this is what we call Horn description logic. So DL light and EL are particular members of Horn description logic. And today there are many work on Horn description logic to solve the ontology-mediated query answering problem. So why do we call this logic Horn? Well, it's very simple. I will show it on an example. So let's consider an EL axiom, which is like this: C and exists R dot top included in exists S dot exists R dot B. What does it mean in logic? It means that for x, if x is a C and there exists, if x is a C and there exists y, so that x is related by R to y, then there exists U, such that we have S of x U, and there exists V, such that we have R of U V, and V is a B. Yes?
What's the true sign? I mean,
This?
not the T.
Excuse me. Top it means anything. It's a. Actually, it's not here. I did not translate it because we don't need it. Okay. It only, so if you say exists R dot T, because it is like this in this description logic, you have to write it like this. But you have the equivalent in DL light. For instance, you will only write exists R. Okay. Because this is the always true symbol, so it doesn't add anything interesting. But it is the syntax of EL imposes that we write it like this. So a more usual form for a rule will be for x for y. If C of x and R of x, y, then there exists U and V, such that S of x, U and R of U, V, and B of V. Now we can put this formula in Prenex form. That is, we can put all quantifiers in front of the formula so that their scope is the remaining atoms. And for instance, we can obtain this. So I will not detail the computation, but for all x, there exists u, there exists v, for all y, etc. And here I have replaced the implication A implies B by not A or B. And then we can colonize. If we want to, we cannot obtain here a clausal form because we have these existential quantifiers. So if we want to have only universal quantifiers, we can colonize this formula. And then it is well known that the obtained formula is not equivalent to the previous one, but they are both satisfiable or unsatisfiable. So here I can replace u and v by Skolem function. We see that u and v depends on x. So when we skolemize, we will replace u by the Skolem function of x. So u is replaced by f1 of x. And similarly, v is replaced by f2 of x. So this is a standard way of skolemizing a formula. And then we obtain for x for y, not c of x, or not r of x, y, or s of x, f1 of x, and r of f1 of x, f2 of x, and b of f2 of x. So this yields 3 on clauses. So I recall that a on clause is a clause with at most one positive literal. So a on clause actually corresponds to a positive rule. And so we obtain 3 on clauses. And that is why we call this description logic on description logic. Because if we take the axiom, we translate them in first order logic, then we skolemize the obtained formulas, we obtain a clausal form. And a Horn clausal form. So now, actually, this kind of formula is what we call an existential rule. And this is the second language, family of languages I want to introduce here. So what is an existential rule? So it is directly in first order logic, so you have no translation effort to do. It is a positive formula of the form for x for y. Body of xy implies there exists a z, head of xz, where x, y, and z are sets of variables. So in the body and in the head of the rule, you have any positive conjunction of atoms with variable and constant, but no other functional symbol. And the particularity of these rules is that you may have variables in the head that do not occur in the body, and these variables are existentially quantified. For instance, we can say that for all x, if x is an actor, then there exists a z such that x plays in z. Or for x for y, if x is sibling of y, then there exists, they have a common parent, so there exists z, who is a parent of x and a parent of y. And later in the example, I will simplify by omitting the universal quantifier and just keep the existential quantifiers for readability. And the key point with this rule is that we can assert the existence of unknown entities, like here with the exist z. Because if we consider a positive rule without the possibility of having variables in the head that do not occur on the body, this rule can only do inferences on the individuals which are already in the fact base. But if we want to, for ontological languages, if we make the open world assumption, the open domain assumption, we would like to be able to reason about individuals which may not be encoded in the fact base. So we don't want to reduce the domain to the individuals that are encoded in the fact base. And this is judged as a crucial feature for ontological knowledge. And just for, I want to mention that this exists also in database theory, and they call that value invention. So I will detail a bit about existential rule, and first come back to the notion of a fact base. So previously I said that the fact base was a set of ground atoms. But if we consider existential rule, we are led to generalize this notion into by allowing existential variables. So why? Actually, why? Because usually in rule-based system, a fact can be seen as a rule with an empty body. So here, if we consider a rule with an empty body, you have an existentially quantified conjunction of atoms. So in line with that, we consider that a fact base is composed of existentially quantified, an existentially close conjunction of atoms. So this generalizes the classical notion of a ground atom. And this is very convenient because it allows to model easily unknown values in databases. So for instance, here you have a relational database with a relation movie, another actor, and another play, which says that some actor plays in some movie. I have the same kind of knowledge encoded in RDF, the semantic web language. And if I abstract this in first-order logic, I will translate, as I said, the relational database can be seen as a fact base. So I will translate each tuple in a table into an atom. I will have, well, actually here I translate only this part. M1 is a movie, M2 is a movie, X is a movie, A is an actor, B is an actor, C is an actor, A play in M1, A play in M2, and C play in X, which is unknown, but we know that X is a movie. Yes, I will also emphasize that a fact or a set of facts can be seen, well, as a set of atoms, but also as a hypergraph. It is very natural to associate a hypergraph to a set of facts. Or if we don't want to draw the hypergraph, because it's not very readable, we can associate bipartite multigraph in which there will be one node per term of the formula, and there is one node per atom, and an atom corresponds to an hyperedge in the hypergraph. And for instance, on a small example, we have P of X, Y, A, X, and R of X, Y. So we have three nodes for X, Y, and A. So we have three nodes that represent terms. And we have two nodes that represent atoms, or hyperedges. The first one is labeled by R, and it connects X and Y. The second one is labeled by P. It connects X, Y, A, and X. So we can associate to a set of atoms, a hypergraph or a bipartite multigraph, in which the edges antecedent to an atom node are totally ordered to keep trace of the order of the terms in the atom. And it exists because I will use later the graphical view of formulas. And so what is it? Ah, yes. So this will be the graph associated with this set of atoms. So for instance, play AM1 is encoded here, play A AM1. And if we have only unary and binary predicate, we can get rid of the atom nodes and replace them with directed edges with labels. And this is a classical notation, in particular in description logic. So we have here the nodes that represent the terms. And relation is represented by a directed edge with a label. And once we have this notation, we can see that homomorphism we have defined with each set of atoms actually is very similar to homomorphism from between graphs. So homomorphism is a classical notion in graph 2. So let us consider that we have two graphs with set of vertices V1 and V2 and edges A1 and A2. And homomorphism from the graph G1 to the graph G2 is classically defined as a mapping from the set of nodes of G1 to the set of nodes of G2 that preserves edges. That is, for each edge UV in the first graph, there is an edge between the image of U and the image of V. And for instance, here you have some graphs. There is a homomorphism from this one to these two graphs, and then a homomorphism from these two graphs to this one. And these two are actually equivalent in terms of homomorphism. So homomorphism may not be one-to-one, but it preserves the path, actually, in the graphs. So, for instance, here, you can map this graph to this one by mapping the first and the last node to the same node. And the homomorphism notion I defined of set of atoms exactly corresponds to this notion. Because I assume we can represent set of atoms as we can see them as graphs, as level graphs. So the notion of homomorphism between set of atoms is the notion of homomorphism between graphs with something atoms which are labels. So if we have labels, we have to keep this from here. This is a representation of Q. We say find all nodes who play in a movie. We have three answers. This is a representation of the fact base, and we can try to find a homomorphism from this query to the fact base. So which maps these blank nodes, which are without constraint, to nodes such that they are related by play, and the second node is a movie. So we can see that we have three answers here, A and A1, A and A2, and C, and this node movie. Well, this is the same with NRE predicate. And we can also see differential rules as graphs, because the body and the head of the graph are sets of atoms, so we can see them as graphs. And then a rule is a graph with two colors. One color for the body of the rule. So for instance here, if we have all X or Y implies like this the parent of ZX and parent of ZY. We can, so the body of the rule is X, S, Y, and the added atoms are represented here. So the head of the rule is composed of the gray node plus this node, which are shared between the body and the head, and we call this node frontier nodes. So in a head of the rule, we have two kinds of nodes. We have frontier nodes, which are the nodes shared with the body of the rule, and existential nodes, which correspond to existential variables. Now, how do we apply a rule? So we take again the same rule. We have a fact that says that A is sibling of B. So here is the graph representation. So we can see the logical representation or the graphical representation. Then it's very classical. We say that the rule is applicable to a fact if there is a homomorphism. So homomorphism again from the body of the rule to the fact base. So here we have the homomorphism that maps X and Y to A and B. Then to apply the rule, we take the homomorphism, we apply it to the head of the rule. So this is very classical. The only thing here is that we have existential variables that do not occur in the body. So for each existential variable in the head of the rule, we create a new variable. So here we will obtain the new fact. So we apply the rule, we create a new variable Z0 for this here, and we obtain a new fact base, which is there is Z0, is that A is sibling of B, Z0 is parent of A and Z0 is parent of B. So, what do we have in this framework? So I try to show you that we can have a logical or a graphical view of this framework. And for each view, the basic notion is that of homomorphism between sets of atoms or homomorphism between graphs. And in this framework, so we have conjunctive queries, we have data files, and in the ontology we have two kinds of knowledge. We have pure existential rules, the one I just showed you. We have equality rules, which can express, for instance, the functionality of relations, like here. If you want to say that a movie has a single director, you can say for X, for Y, for Z, if Y is a movie and X is director of Y and Z is director of Y, then X is equal to Y. And we have negative constraint, which forbids some situations to occur. Like here, express that movie and person are different concepts. But in the following, I will focus on pure existential rules. So where does this language come from? I will do a bit of history. Well, very recent history. We are only back to 10 years ago. So actually, these rules come from two different research lines. In my group, we were working on graphs. That's why I show you graphical representation of all that, because we started to work on graphs, actually on conceptual graphs that were first introduced by John Sova in 1984, and then we worked on this graph to develop the knowledge representation and reasoning language, completely based on graph and graphical operations, but with a logical translation. And if we translate the graph rules into first-order logic, we exactly obtain existential rules. And at the beginning, we called this for-all existential rules, and then in the community, the term existential rules has been coined. And another research lines come from a database theory from Georg Gottlob. And what they wanted to do is to extend Datalog. So Datalog is a querying language for deductive databases. And in a Datalog rule, you have in plain Datalog, you have the constraint that all variables that occur on the head must already occur in the body. So you cannot invent new individuals like with existential rules. So with the aim of representing ontological knowledge, they extended Datalog with the possibility of having existential variables in the head. So this means exactly existential rule, and they call this Datalog plus. And then they divide several members of the family obtained by restricting Datalog plus. So the whole family is called Datalog plus minus. And actually, existential rules have a long history because they have the same logical form as very general constraints used in database theory, which are called tuple-generating dependencies. And these dependencies were defined, I guess, beginning of the 80s. But they were studied as constraints for databases. But anyway, they have the same logical form, so there are many theoretical results that carry out, obtained in this field that carry out on existential rules. And now, if we consider the lightweight description logic I presented you, Horn description logic, or for those who know the semantic web languages, for instance, all two tractable profiles are Horn description logics. Well, Horn description logic can be seen as particular existential rules. What we get when we go from light description logic to existential rule is the possibility of having unrestricted cycles on variables and an unbounded arity, because description logics are limited to unary and binary predicate. And this explains that many people from the description logic community have begun to investigate existential rules as well. So it's still on the comparison between on description logic and existential rules. We have seen that the first order translation of on description logic yields existential rules. Existential rules are strictly more expressive. Why are they limited when they want to describe interaction between variables? Because the formalism has a variable tree syntax. So basically what we can describe is trees. And for instance, if we don't have role composition in the description logic, we cannot express things like this. For all x, y, if x is sibling of y, then there exists z, which is parent of x and parent of y. Because this rule makes a connection like this between x, y, and z. And this is a kind of cycle we cannot express in description logic except if you have role composition. So here I took a very simple example, but even if we have role composition, we cannot express any cycle between variables. Because here you can see we introduce a z, but we can say nothing about this z. So more complex interaction between variables cannot be expressed in description logic. And in existential rules, you moreover have unbounded predicate arity, which allows for more flexibility. We have seen that the database can be directly translated into a fact base in the existential rule framework. And it's very easy, when you have unbounded arity, it's very convenient because it's very easy to add contextual information. For instance, if you want to add information about provenance, trust, etc., you just add a new argument to your predicate. And you can encode naturally this information, which becomes very complicated sometimes in languages where you have only binary predicates.
I'm sorry, what is the definition of unbounded predicate?
Unbounded predicate arity, I mean you can have any arity, any number of arguments in a predicate.
But do you consider the arguments as a tuple or in some other way?
Yes, I see the arguments as a tuple. So for me, a predicate is a relation with an arity, and each predicate has a fixed arity, fixed number of arguments. And unbounded predicate arity only means that you can have any arity you want. And in description logic, you are limited to binary predicates. But, so it looks very nice, but of course, unsurprisingly, this added expressivity has a cost. Because if we consider general existential rules, the fundamental decision problem, which is given a Boolean conjunctive query, is this conjunctive query entailed by knowledge base in the existential rule framework. This problem is not decidable. And it was shown a long time ago on tuple generating dependencies, a similar problem for tuple generating dependencies. And we have shown also that it remains undecidable if we have a single rule. So this is not good news, but these last 10 years, there have been a lot of works to find decidable classes of rules. I mean classes of rules for which the problem is decidable and even tractable in terms of computational complexity. So decidable classes of rules with good expressivity, tractability traits. And here is just a partial map of decidable classes. So don't worry, I will not detail this today. But what I wanted to point out is that up to the beginning of 2000, there were only 3 classes of existential rules known for which the problem was decidable. Of course, they were datalog, because in datalog there are no existential variable at all. And they were conditions on tuple generating dependencies, which are called weakly acyclic. I will train this tomorrow. And we are using also acyclic condition and conceptual graph. So we had only this. And from 2008, all these classes have been designed with very different principles that ensure the decidability. And this is only a partial view of the main classes of existential rule with decidable coherence. And here you have the whole description logic I mentioned. So you see that they can be seen as specific cases of very simple existential methods. So I don't know, maybe I will stop here because now I wanted to explain so maybe, well, I think I cannot explain this in a few slides, so maybe we can stop here.
Okay.
Yes, just some practical information. We want to participate in a gala, diner gala on the Sunday 24 January at the City Palace. You can go to pay the payment. That is right. You want to participate at diner gala.
Yes.
On the Sunday 24. You can go right now. The payment at the reception desk. That is right.
Okay. Can I ask a small question?
Yes, of course.
What do you do if in your relational database the relations is partial, so not all attributes have values?
Yes, that's what I think. Yeah, I showed in. Here. For instance, here you have a database with unknown value. So we simply translate unknown value as existential variable. And this is very natural in the control framework because it corresponds to a rule with an antibody.
Maybe the same again.
Other questions?
What is the size of the database beyond which it's not decidable? I suppose there is a size.
Well, no, it's not depend on the. It doesn't depend on the size of the database. If the database is large, you may be more or less efficient. But this undecidable means that there is no algorithm that is guaranteed to stop. So it does not depend on the size of the database. It depends on the complexity of the rule language. And then about size of databases, well, it really depends on the complexity of the rule language.